This is Bri Murray and I want to welcome you to another episode of Doc Bri, the Physics Guy. Hi everyone, today we're doing the expanding universe. Before we get started, we're making a couple of assumptions here. Depending on your view of certain things, you may or may not agree with any of this. It's one of those things that makes physics cool. Today, we're working on the idea that there was a Big Bang about 13 million years ago, and the universe has been expanding from this Big Bang ever since. Recent experiments seem to show that the universe is actually expanding faster than we initially thought. In fact, the universe is actually accelerating in its expansion. There are some people, though, who doubt these results and think they might be wrong. But for now, we're working on the idea that the interpretation of the results is correct, and we really are in a universe which has an accelerating expansion. Cool. This causes a bit of a problem now. In a previous post, I mentioned Newton's second law, and this law basically says that to accelerate something, you'd have to give it a shove. There has to be a force. So the question then arises as to what is actually giving the universe a shove. If it's accelerating, there must be some force in play. I have no problem with the accelerating, expanding universe idea. I quite like it because it gives us something to think about. It's not supposed to be that way. I mean, it wasn't that way when I was a kid. It was just expanding, but not accelerating. So we must have something wrong. It's just a question of what? One of the ways we measure the speed that galaxies are receding uses a technique called redshift. This can be explained as the Doppler effect on light. All atoms emit light radiation at very particular frequencies. We imagine that this electron is dropping from an excited state to a lower state, and as it does, energy is ejected, it's emitted, and this is what we see as light. This amazing property I'll cover elsewhere because it allows us to determine some of the elements in stars. I mean, just how amazing is that? Coming back, if a star is moving away from us, then it was discovered that the frequency of the emitted light tended to be shifted slightly towards the red end of the spectrum. Taking this a step further, it was realised that the amount of this shift was dependent on the speed that the star or galaxy was receding from us. The faster the stars and the galaxies are receding, the greater the redshift. This is not all though. Oh no, my friend. See, there's more. We know that the universe is expanding. Hubble proved this back in the day, and it was soon realised that there may be an additional redshift due to the fact that gravity can cause redshift in light. An explanation for this can be found in general relativity, and experiments show that it's real. Basically, the higher the gravitational field, the greater the redshift in the light escaping. Now, I could be wrong about this, but it seems to me that if we assume that space-time is the same as flat space are those regions where there's few stars, the space between galaxies, and there's an awful lot of this, by the way. Seriously, there's a lot of the universe that just appears to have practically nothing in it. You want to find something close to the perfect vacuum, deep space. We're looking at one atom in a cubic metre of space. Compare this with the best vacuum ever achieved on Earth. The best vacuum we've achieved on Earth has about 100 million atoms per metre cubed. And that is a fantastic vacuum, by the way. There is virtually nothing in deep space. I mean, I'm serious. Talk about the void. This is it, mate. And the amount of it is beyond the imagination of everyone. You might think you've got a great imagination, but it's nowhere near capable of imagining the vastness of deep space. Another thing is that we're working on the basis that our interpretation of the current observations of redshift are correct. In other words, the theories are correct. Okay, so let's tackle this in reverse order. Let's say that the theories are correct. Well, we've got a problem right away. Almost all of the current theories are bound to be wrong. They already have so many things wrong with them. There are already so many things that our theories can't explain. Small galaxies that appear to have supermassive black holes, 4 billion solar masses no less. Galaxies that don't follow Newton's law of gravity even though they should. some galaxies that appear to have more mass than they should. All of this, and this is just a few examples, have given rise to the idea of dark matter and dark energy. So are they correct? Probably not. So if they're incorrect, then chances are we've probably also got faults when it comes to redshift. Yeah, I know this is a bit of a cop-out, but I genuinely think that the way we're measuring redshift may have issues. And this brings me to point 1. I was once on a ship that crossed Drake's Passage. It's an area of sea south of Argentina, and it's named after Francis Drake, an English privateer, which is a posh word for a pirate, who knew a thing or two about sailing. Now this sea is where the Pacific meets the Atlantic Oceans. Now to the ignorant, namely me, sea is just sea. It's water, salty water. This is not the case though. See, there is a very clear point where the Pacific meets the Atlantic, and the salt concentration in the water is different between the two seas. Not only that, but where the world meets Antarctica, there's a detectable sharp drop in the temperature of the water. Now this was a real revelation to me, because I'd wrongly assumed that seawater was pretty much the same. Not so, and this got me pondering. See, it occurred to me that something similar could happen in space. Imagine regions that have a greater concentration of energy than another region, much in the same way that galaxies contain a far greater concentration of mass than deep space, where there's practically nothing. Now, I would have thought that given enough time, the balance of salt between the Pacific and Atlantic Oceans would balance out. But no, something, probably the Amazon basin, is reducing the concentration of salt in the Atlantic so that it never matches up to the Pacific Ocean. Now again, imagine if something like that is occurring in space. So one region is continually being topped up or depleted compared with another. Now if something like this did take place, then the regions of space-time may actually be different, and their properties with regard to the way light propagates may be different. My thinking then is that the results we see may be erroneous, because we're assuming that space-time is linear and constant in the regions of deep space, when actually it might not be. Imagine if there was a similar sharp change between space-time depending on where you are in the universe. I mean, this is the sort of thing where dark energy comes in, because this may be the thing that produces this variation. So to try and sum this one up, what I'm saying, and I am sitting on the fence a bit here, is that the idea of a universe expanding faster than it should could actually be wrong. Let's say the observations are clear, so maybe our interpretation of them may be skewed, because space-time isn't flat, even in deep space. You can have two flat regions of space with a clear gradient between them. This gradient, or the different nature of the regions of space-time, causes some of the light shift itself, thus distorting the results. Now this may also show up as dark energy, but rather than it being everywhere, it might only be in certain areas. The truth is, we don't really have any idea what's going on, which is great, because it's still the undiscovered country. And who knows, maybe you'll be the one to figure it out. I doubt I will be. This is Dr. Bry, the physics guy. Hey everyone, this is Dr. Bry, the physics guy. I hope you enjoyed this episode. If you did, can you share it with your friends, your fellow students, and anyone you think might be interested? That'd be great, and you'd be doing me a massive favour. Subscribe now so that you don't miss out on the latest episodes and news, and check out my website right now at drbry.com. That's drbry.com. And for a limited time, I'm giving away the first part of my 7 ingredients course. It's absolutely free. There's almost 40 minutes of free video explaining the course and why you have what it takes to do physics and how it can change your life forever. And there's also a free download that you can keep. All the details are on my website. I'm also on YouTube, Instagram and Facebook, and all the details are there on drbry.com. drbry.com. I look forward to seeing you soon.